Okay, hopefully I'm having technical problems today, so wish me luck. Alright. Okay, alright. We talked about exponential functions. Okay, exponential growth and decay. I'll have an initial amount. I'll have a factor. Here's my exponential function. Have a factor here. It could be growth or decay to the x power. It's an exponential function because my variable is the exponent. All right. B has to be greater than 0, but it can't be 1. Greater than 0, but not 1. A can be anything but 0, but when we do growth decay functions, whatever we start off with is normally positive, okay? All right, so I've got something growing at 6.5% per year or per month or whatever. To figure out my growth factor growing, I turn this into a decimal. I turn this rate, this growth percentage to a decimal, 0.065. It's 1 plus r, the decimal version of the percent, and I get 1.065 right here, okay? So we're going to add 1 plus r. Remember, I'm not going to multiply by 0.065 or 0.6.5. You have to convert that. It's like having, a tax on something. It's 8% sales tax in Texas would be times by 1, your amount times 1 to keep the initial amount plus the 0.08, so 1.08. Anyway, convert your growth. It's always going to be your factor, be 1 plus r, or in decay, 1 minus r. So here's a decay version. Something's decaying at 7.2% per year. To get a decay factor, I take 1 minus that. Decimal r is the rate in decimal form. 1 minus 0.072 gets me 0.928. So if I multiply something by less than 1, it's decaying. Okay, that 0.928 is the decay factor that reflects 7.2% decrease. Okay, which would be 1 minus 0.072. All right. Remember, if you got something decreasing at 20%, you multiply by 0.8. If you have $100 times 0.8, that's $80. That's minus 20. Or 20% drop. Okay, so remember to do the 1 minus r, 1 plus r to get your factor. Okay, notice here's growth, decay. This is when b is greater than 0 but still less than 1. Transformations of exponential functions. Remember, horizontal will take place up here. I'm messing with the input. Plus or minus is a horizontal shift. Minus, remember, it's backwards. Minus is right, plus is left. Vertical, up here, this is after I've done the function, so I'm really affecting the output. So I'm either once I do the function, take 2 to the so-and-so power, then I can plus or minus. Remember, plus is up, minus is down. This would be a vertical shift. And when you multiply, remember, shifts are plus or minus. Multiplication is stretch or compression. Here I'm multiplying, I have an a value of 3. This will stretch this graph greater than 1. These values get multiplied, it'll stretch it on up. If this was a fraction, like 1/30, 1/2, all these values would come on down and be flattened out, be compressed, okay? So horizontal shift, vertical shift, this will be a stretch. If it's greater, if it's greater than 1, if it's a fraction, it'll be compressed, okay? All right. Remember though, up in the exponent is where your horizontal shifts occur, okay? Left or right. Exponential functions and logarithmic functions are inverse. Here, remember they have inverse, so this domain is this range. This range is this domain. Here I plug in an exponent, I get an output. Here I'm plugging in that output and I get the exponent. Here's an example. So here's 2, base 2, I plug in 4, I get out 16. 2 to the 4th power is 16. To inverse all this, I take the log base 2. Remember when we solve for exponents, we take the log. What's the exponent that 2 is raised to get 16? Log base 2. Here I plug in 16. Notice I plug in the output as my input, and I get out of 4. Okay? Notice 4, get out of 16, plug in 16, get out of 4. Okay? Notice this domain is, the domain and range is shift, okay, or flip-flop. This domain is this range, and this range is now that domain. Okay? Logarithms. A couple ways this is about my 5th take on this. Sorry. Okay, sorry about that. My dog went ballistic. My daughter came home. All right. Okay, logarithms. I've got Couple types here. Watch it. Let me just zoom in here. Okay. All right. So here I've got 4 to the x plus 2 equals 1 over 8. It's I've done so much work here. Look for a common base. Okay, there's one type of logarithm problem is you don't see a log anywhere here. I've got 4 to the x plus 2 equals 1 over 8. Okay, one way to solve this, get the common base. I noticed that 2 is a base for both these exponentially. I rewrite 4 as 2 to the second power. I rewrite 1 over 8 is 1 over 2 to the third, and then when it comes up in the numerator, it's 2 to the negative third. Okay? So remember, raising a power to a power, I have to do this. 2 times x and 2 times this whole thing. So I get up with 2x plus 4 equals this negative 3. So when you get to like bases, once you get to like bases, the exponents have to equal each other. Because they've equaled each other. These equations have equaled each other. This side and this side have been equal all along. We're just rewriting them to a same base, and once you get a common base, the exponents equal each other, and you solve. Okay. Another time where you don't have, like here, I've got 6x to the 73rd equals 6x equals 73. Remember, I don't have a log here either, but I don't have a common base, so I'll take the log of both sides, and what happens is I get log of 6 equals log of 73. But when I take the log, the exponent comes down, and we just divide out, and x equals log of 73 over log of 6. Okay? All right, so here's two types of us to have logarithms, or logarithmic problems where we don't have a log written anywhere, but we can solve for it here with common bases, here by taking the log of both sides to get the exponent down. Now, a couple other problems. Here I've got log base 2 of 3x minus log base 2 of 4 equals log base 2 of 6. Notice I've got log on both sides the equal sign, okay? So I'm going to set log equal to log, but first simplify. Remember, subtracting 2 logs is the same as a single log with division. So it's 3x over 4. Log of m minus log of n is single log of m over n, okay? And that equals what? This log base 6. So remember, this is saying, hey, a log is an exponent. This exponent equals this exponent. So both this 2 and this 2 are raised to the same exponent, so hence this equals this. So you're going to set up 3x over 4 equals 6, multiply both sides by 4, that's 24 equals 3x, x would be 8, okay? So when you get log on both sides, you set it up to have log equal log, and you set up whatever you're taking the log of equals each other. A final type we've had is just a log on one side. Again, simplify. Here's the multiplication where log plus log, you simplify that into multiplication, okay? The log of m plus log of n equals a single log where this is multiplied m times n, or 8x times, that is a 4, not an 11, okay? All right, so that would be log of 32, log base 2 of 32x equals 6. And here, this is kind of knowing from our exponential logarithmic work we just did recently. Remember, I've got a base and exponent. Rewrite this as an exponential function. 2 to the 6th power equals 32x. That's 2 to the 6th power is 64 equals 32. X is going to be 2. Okay? Simplify your logs to multiplication or division. When you've got it on one side, you write an exponential equation. Okay? Base to exponent equals that. When you've got log on both sides, you set whatever you're taking the log of equal to each other. And up here, you can either do get like bases or take the log of both sides. In this case, like bases is easy option. Log of both sides is an easy option. Okay, parent functions. Remember your parent functions, you need domain and range. Y equals x squared. Remember, domain, all real numbers, and range, all real numbers. Y equals x squared, domain, all real numbers, range is 0 or greater. Absolute value, domain, all real numbers, range, 0 or greater. Okay? Y equals x cubed. My domain and range are both all real numbers. Think about things. Here's concavity. Concave down, inflection point, concave up. Always concave up. decreasing from here to here. From negative infinity to 0 is decreasing. From 0 to positive infinity, it's increasing, okay? Root function. Domain and range are basically the same. Domain is what? X is greater than or equal to 0. Range is Y is greater than or equal to 0, okay? 1 over X. This is the one function that's always decreasing. This right here is concave down, always increasing. This is always decreasing from my domain. As X increases, Y decreases. And again, there's no domain here at 0. So again, we start over fresh. As X increases, Y decreases. So this is always decreasing function, but from negative infinity up to, not including 0, concave down, here's concave up. Exponential. Remember, domain and range are going to be inverse to the logarithm. But here, all real numbers for my domain, range is greater than 0. And now here my domain is greater than 0. Notice this graph on the x-axis is greater than 0, but my range is all real numbers, okay? And here's y equals 1 over x squared, the reciprocal squared, okay? Domain, negative infinity up to not including 0, and from greater than 0, okay? So less than 0 and greater than 0 is my domain, and range is greater than 0. All right, let's talk about absolute. Remember, absolute max and mins. Absolute max occurs right here. This is my absolute greatest value. It occurs right here at this x value. Okay, I didn't ask what it was. I just, where's all these things occur? All right, I have an absolute min value right here at this x value. Okay, absolute min, absolute max. If they ask what it is, then you can give the y value. But you're really going to say, where's the x coordinate? I haven't. Most people and most so far we're more concerned with where it occurs, and that's where I've been asking you on tests and the worksheets. Where does these absolute max occur? What's the x value? Okay. All right. I have relative max and mins where I have change in slope. Here's a relative max where I have an upslope, downslope. Here's a relative min, downslope, upslope. This is not a relative max because there's no change in slope. Okay, so let's look at all our so here's my absolute minimum occurs here, my absolute max occurs here. I have relative minimums here. Right here, change in slope. Right here, change in slope. So here's a relative min, relative min. Here's a relative min. Okay, right here, it occurs right here, downslope, upslope. I have relative maximums, not here, no upslope, okay, but I have relative max here, relative max here, and this is not a relative max because I don't have any slope down here, it ends, okay? All right, concavity is where we change from smile to frown. Inflection points is where we change from smile to frown. Concavity up, concave up or concave down. Okay, concave down is a frown. All right, this is not an inflection point. There's no concavity here. Okay, so here's a frown, but right here is an inflection point. It occurs right here, and then it's smile till this point at x equals 0. So here's an inflection point, and then we turn from a smile to a frown. Here's an inflection point and this is not an inflection point because there's no concavity here. You have to change concavity. All right. So we talked about absolute max, absolute min, relative max, relative min. The difference in relative and absolute is relative. You have to have the change in slope. All right. And finally, domain range. My domain for this graph on my X highway, what mile markers do I start getting a graph? From here to here. This is whatever this is. A to B, union from C to D. So A comma B, union C comma D. Okay? All right? Let me kind of zoomed in. All right? Now let's do range. I'm going up the Y highway. What mile markers do I have where my graph occurs? From here, let's say from E to F, I've got a graph. So from E to F, union G to H. From this mile marker to this mile, I've got a graph here. Okay? All right? So that's about it. There's 15 minutes. Got to go. Good luck on the CBA.